Hi guys, so in this video we're going to look at the strengths of acids and bases in terms of their equilibrium constants and in terms of their ionization and dissociation strengths. So first of all, something that you need to know is when we look at an equilibrium reaction, you always start with reactants, okay? And the reactants then can undergo a forward reaction and as well as a reverse reaction. Okay, and we're going to talk more about equilibrium and the definition of equilibrium. But for now, you just need to know that this reaction can proceed forward in a forward manner to produce products, and it can also go from products back to reactants. And that's basically what's happening when we look at the ionization of a strong acid and of a weak acid. So when you have a very strong acid, you will have complete ionization. And this basically just means that the concentration of your hydronium ions, this concentration is going to be much higher. Okay, and that is because of the complete ionization. So when you draw in the equilibrium arrows, you will have this arrow for the forward reaction will be more than the arrow that is pointing backwards for the reverse reaction. So this will indicate that the reaction favors the forward reaction. So the equilibrium favors the forward reaction, and therefore you have more hydronium ions and more chloride ions than your reactants. So when we write a Ka-Kb equation, so remember that for equilibrium reactions, whenever you write your equilibrium constant, it is always the concentration of products over the concentration of reactants. Now, you never write this down as a formula, but it's just to help you remember. And remember, in an equilibrium constant equation, you're only allowed to write in certain states. So, for example, ions or molecules that are in aqueous state, or that are in gas state. Okay, we never write down if something is so not for liquid or for solid. Okay, so it's only with those two states. So when we comprise the Ka, now the A is just for acid. So the Ka equation for this reaction is going to be the two reactants, the two products in this case. So that will be hydronium ion concentration times that by the chloride ion concentration, both aqua. So we can write them in the Ka expression. Divide that by the concentration of HCl, which is in a gas state. We do not include the water in our Ka expression because water is a liquid. Okay, and that's basically what you need to know for this expression. If we had, let's say, a different scenario where we worked with sulfuric acid, let me just get a different color. Let's say I have sulfuric acid, right? And it is now also ionizing in water to form sulfate ions and to form hydronium ions. It is always important to ensure that you have a balanced reaction equation. If you find this a little bit difficult to balance, you can always just write down hydrogen ion. Okay, it's the same as saying hydronium. And because you can see the acid gave away 2 of its protons, that has now a molar ratio of 2 as 2, 1. Okay, so when you write down the expression for this acid, that's also aqua, and this is also aqua, you will write down hydrogen ion or hydronium ion with the molar ratio as an exponent, times that with the sulfate ion divided by H2SO4. Okay, so that was a good practice round. So whenever you see different molar ratios, okay, remember that that has to then be written as the exponent. Okay, so don't forget that. Right, let's look at the ionization of a weak acid. So in this case, acetic acid. Now remember that weak acids will not ionize completely. So it's incomplete ionization. Ionization. Okay, which means that the hydronium ion concentration is not actually going to be that high. Okay, that's why you would expect a pH that's not as low as with a strong acid. So the hydronium ion concentration is not as high, okay? But it is still higher than, for example, if you had a base. Now in this case, when you write down your equilibrium arrows, the forward reaction is not going to be necessarily the strongest or the most favored reaction. Okay, it can be a combination of both. Okay, but the reverse reaction is actually also favored. Okay, whereas if you compare that to a strong acid, the forward reaction was definitely favored. So if I can quickly write down my Ka expression for this, write down the concentration of my acids, that's aqua. Okay, I see that should be aqua, the hydronium ions, and we are going to divide that by the concentration of the acetic acid. Okay, so that's going to be the Ka expression for a weak acid. Right, if we move over to bases and we talk about dissociation of a strong base. So with a strong base, you will have complete dissociation. Okay, so instead of working now with Ka, we're working with a Kb. And the same will apply with the equilibrium. The forward reaction will be more favored than the reverse reaction. So if you write your Kb expression, the concentration of your products will be higher than the concentration of your reagent. So you have sodium and you have hydroxide. Okay, now remember that in your expression you only put aqueous and gases, not solids. So this will not feature in your Kb expression. And you can see based on what you have here is that your dissociation constant will depend on the concentrations of each of these respective ions. Okay, if you have a very weak base like magnesium hydroxide, your reverse reaction might be favored more. So you don't have complete dissociation, so it's incomplete dissociation. Okay, so if we write an expression for that, Kb will then only be equal to the magnesium concentration. And now look at that. You have a molar ratio of 1 to 2. So 2 hydroxides for every 1 magnesium ion. So when you write that in your expression, remember to put that 2 in as your exponent. Okay, and that will be the respective dissociation constants. So if I can just quickly recap, if you go back to the meaning of these expressions, okay, the ionization constant and the dissociation constant. If I, for example, look at this reaction, and if I told you that I have a very, very high concentration of hydrochloric acid, and they ask you to explain what is the effect that this will have on the Ka. Is your Ka value going to increase or is it going to decrease? So if the concentration of HCl is very high, that means that the relationship, because if you look at the expression, you can see that Ka is not directly proportional, okay, it's irreversely proportional to the concentration of hydrochloric acid. So in other words, as my concentration of hydrochloric acid increase, my Ka value will decrease, okay, because it's a fraction. So 1 over a very high value will give you a very small value. And they could ask you the opposite. If this concentration is very low, then the Ka value will be very high. Okay, and the same with all the other expressions. They can ask you to explain, let's say for this reaction, same thing. They can ask you to explain if this concentration is high, what will happen to the value of Ka. So if this is high, a very high concentration, then your Ka value is going to be much smaller. Okay, and the reason for that is, remember, if this concentration is very, very high, then and we will learn about that in Le Chatelier's principle, but then more of this is going to be shifted towards the other side, right? And that will then favor your forward reaction more. So that will mean that these concentrations will then increase later on as the equilibrium starts to establish itself, okay, or work against the change. So that was that for the strengths of acids and bases. Stay tuned for the next video on the pH scale and then also pH calculations.